Hello everyone, and welcome to this session at the Autonomous Robots and Multirobot Systems, AAMAS, workshop. My name is Ilya Afanasiev, representing Innopolis University and St. Petersburg Electrotechnical University, LETI. Today, I am excited to present my research titled Beyond Kalman Filtering, a dual Quaternion geometric observer for robust 6 degrees of freedom pose estimation. In the context of multi-agent systems and autonomous agents, reliable, drift-resistant, and computationally lightweight navigation is a foundational requirement, especially when agents operate in complex GPS-denied environments. This research proposes a fundamental shift away from traditional covariance-based filters toward a purely geometric, manifold-aware observer approach, specifically tailored for resource-constrained edge devices. Accurate pose estimation is the absolute backbone of autonomous navigation. Contemporary mobile platforms rely heavily on fusing high-frequency inertial measurement units, IMU, with lower-frequency visual odometry, or GPS. Traditionally, this sensor fusion is handled by extended Kalman filter, EKF, or aerostate Kalman filter, ESKF. However, these conventional methods treat rotation and translation in separate estimation spaces. This artificial decoupling is mathematically flawed for rigid body motion. It leads to severe linearization artifacts, kinematic inconsistencies, and classical singularities, like gimbal lock, particularly during highly dynamic, unconstrained motion. Furthermore, while modern Lie group-based filters, like the unscented Kalman filter on manifold UKFM, offer much better precision, their complex sigma-point transformations make them computationally prohibitive for low-power edge hardware. The core problem remains. Traditional filters fundamentally compromise the intrinsic geometry of rigid body motion on the SE3 manifold, trading geometric fidelity for mathematical convenience. To address these fundamental challenges, I propose the Dual Quaternion Geometric Observer, or GeoDQ, as shown in the architecture diagram. Instead of tracking error states with complex covariance matrices, the proposed observer operates directly and exclusively on the SE3 manifold. The pose is represented as a unified algebraic entity, a unit dual quaternion. This compact representation compactly encodes both rotation and translation, avoiding singularities by design. When asynchronous visual odometry measurements arrive, they are fused using screw linear interpolation, or SCLIRP, rather than linearizing the space. SCLIRP interpolates the state along the geodesically optimal screw path. I augment this geometric update with an adaptive Huber weighting scheme. The alpha parameter aggressively scales the update based on measurement confidence, rejecting outliers automatically without the need for probabilistic covariance tracking. Finally, I integrate a continuous PID-style feedback loop to estimate and correct IMU sensor biases dynamically. Let's look at the geometric observer in action on a highly complex trajectory from the Ronin dataset. On the screen, you see a dynamic 3D trajectory comparison, its top-down projection, and the real-time pose error. Here is a comparison between the ground truth in black, the standard ESKF in purple, the UKF on manifold in blue, and the proposed GeoDQ observer in dashed red. As the sensor undergoes rapid directional changes, conventional filters exhibit significant position spikes. In contrast, this observer strictly adheres to the SE3 manifold invariance, maintaining a smooth, tightly bounded convergence without artificial overshoots. To ensure the statistical validity of this approach, I conducted a comprehensive large-scale evaluation across 35 distinct unconstrained trajectories. This batch video demonstrates the tracking performance across various spatial environments. As summarized in the dynamically updating table on the right, the proposed method significantly outperforms the state-of-the-art baselines. Over the entire dataset, GeoDQ achieves an outstanding average root mean square error RMSE of just 0.0043 meters. Beyond accuracy, the computational efficiency is remarkable. By compiling the algorithm into optimized machine code using number just-in-time JIT compilation, the observer processes an entire trajectory in just 3.05 seconds. This translates to an approximate 7 times speedup over standard filter executions, proving its ultimate suitability for high-frequency embedded platforms. To synthesize the results from the batch evaluation, This table presents the aggregated performance benchmark across all 35 Ronin trajectories. The key takeaways are twofold. First, regarding estimation quality. The proposed GeoDQ observer achieves an incredible average RMSE of just over 4 millimeters. Notice that its standard deviation is also substantially lower than that of the filter-based methods, indicating highly consistent performance across diverse human motion patterns and a greatly reduced tendency to diverge. Second, regarding computational efficiency. While the standard Python implementation of GeoDQ is already competitive, the JIT-optimized version provides a massive acceleration. Processing an entire trajectory drops from 23 seconds to just 3 seconds, an approximate 7-fold speedup. This combination of sub-centimeter precision and millisecond-level execution firmly establishes GeoDQ as an optimal solution for swarm robotics and edge computing. A critical requirement for autonomous multi-robot systems is resilience to sensor occlusions and measurement dropouts. To evaluate this, I performed a global robustness analysis, artificially decimating the visual odometry update interval. The plot on this slide illustrates the resulting error on a logarithmic scale as the gap between position updates increases up to 40 times. Traditional Kalman filters cautiously balance process and measurement noise. When measurements are delayed, their covariance matrices rapidly inflate, leading to severe divergence, as seen by the blue and purple lines. Conversely, the proposed geometric observer eschews covariance tracking entirely. The SCLRP operator acts as a mathematical geometric spring on the SE3 manifold, pulling the state along the shortest geodesic path. Consequently, GeoDQ exhibits a remarkably smooth, gradual error growth, maintaining stable sub-meter accuracy even under severe measurement sparsity. Finally, while GeoDQ demonstrates excellent performance, it is important to acknowledge its limitations and outline future work. The primary advantage of the observer, its reliance on purely geometric interpolation, is also its main dependency. By eschewing probabilistic covariance matrices, GeoDQ assumes a baseline level of robustness in the visual odometry signal. In scenarios with highly noisy GPS or erroneous visual loop closures, the lack of a probabilistic covariance matrix means the observer might aggressively interpolate toward a sudden outlier. To address this limitation, my future work will investigate incorporating a lightweight probabilistic metric into the interpolation scaling factor, allowing it to dynamically gate extremely noisy measurements. Additionally, future empirical validation will focus on high-speed robotic platforms, such as agile drones, to fully characterize the observer's performance under extreme accelerations. In conclusion, this research demonstrates that grounding sensor fusion in the intrinsic geometry of the SE3 manifold yields substantial benefits over traditional filtering paradigms. I introduced GeoDQ, an observer that completely eliminates artificial decoupling and linearization artifacts through dual quaternions and adaptive SCLRP fusion. It provides an optimal balance, achieving superior accuracy while running significantly faster than manifold-aware Kalman filters. This makes it a highly compelling choice for resource-constrained wearable devices, microaerial vehicles, and autonomous ground robots operating in GPS-denied environments. I strongly believe in reproducible research, and the complete source code for the manifold library and the GeoDQ algorithm is publicly available on the GitHub project page linked on the screen. Thank you very much for your time and attention, and I look forward to any questions.